So you're welcome back to the class. So now we are going to continue, and we are going to do the hands-on session briefly on ANN. We are going to be working with the MATLAB as usual. And when we're talking about ANN, we said that you need data, right? So today we are going to be working with the data set, and we're going to look at the data set and so that you can understand the kind of data that you need to get when working with ANN. And if you have a good understanding of the data and the availability of the data, then you can work with it. So the data set we're going to use is called the Pima Indians data set. It's a data set for diabetes, actually, for diabetes, Pima Indians diabetes database. It was gotten from a research center from the Johns Hopkins University. It's a medical research center, more or less. So let me open the data set so that we can see what it looks like. Okay, so can you see my screen? You should be seeing Excel.
Yes.
Okay, good. So what we have here is a data set. Now, what this data set represents is for each row that we can see is a row of an individual. This is a medical record of an individual. Now, from that's from row A to H, you can see different column headings. The first one is there's a data set description. Maybe when I'm posting the data set on the Teams platform, I'll post it with the description. Now, for the first one where you see preg, it means the number of times the patient was pregnant. Where you see plas means plasma glucose concentration. Pressure is the diastolic blood pressure. Then skin is the triceps skin fold thickness. Insu is the 2-hour insulin, serum insulin. Mass is the body mass index. Then PEDI is a pedigree function. Age is, of course, the age. So these are values of each individual. Now, the class is the target or the labels that we were talking about for supervised learning. 1 means the person has diabetes, and 0 means the person does not have diabetes. So each row represents a particular individual. So like the first person, the person has been pregnant 6 times, has a blood pressure of 72, has a body mass index of 36, and the person has diabetes, and the person is 50 years old, right? We can see here there's somebody who is 29 years old, 10 times pregnant, blood pressure. Okay, we don't have it, it's 0 more or less, but the body mass index is 35.3. So different instances, different patients. And we have a total number when we scroll down. We have a total number of 768 instances, because of course, if you subtract the first row that has the title. So 768 patients here. Now for deep learning, this might be too small, but for machine learning, this is more than enough for neural networks. So we're going to use this data set to train a neural network in MATLAB. So that's what we are going to do. Now, the main data is from A to H. This is the main data. Then column I is the class or the target. So please take note of that, because it's going to come in handy when we start the MATLAB. So I'm going to stop sharing the screen with the data, and I'm going to now share the screen with MATLAB. Okay, so can you see my MATLAB?
Yes.
Yes, we can see it.
Okay. Yes. So I'm going to run the codes from the same directory as my data set. So I have the diabetes.csv data set, and this is just a copy of it. And this txt file is just an explanation of the data set. I will upload all of these to the Teams classroom as well. In addition to the video when I'm able to download it. So when you want to work with neural networks on MATLAB, luckily MATLAB comes with a neural network toolbox that you can use that for. And the way to access the toolbox is for you to come to the command window and type nn start. NN start, meaning start the neural network toolbox. NN start. NN START. NN start. When you press NN start and click enter, it will load. I think it should take some time in my case, but when it loads, it will come up with a pop-up of the options of what you want to do when it comes to the neural networks. So, okay, so it has popped up, but I don't think you can see it until I share it again. So, can you see the new window I've shared? The NN Start window.
Yes, we can see it.
Yes, so it's smaller. So what it's showing is that open applications for training shallow neural networks. You know, we said neural networks, you have the deep neural networks, which have a large number of layers. But in our regular neural networks, that the number of layers are relatively small. They are called shallow neural networks. And you have different options. You have input-output fitting, you have pattern recognition and classification, you have clustering, you have nonlinear time series. In our instance here, what we are concerned with is fitting, input-output fitting. We are trying to find a relationship between those inputs that we saw and the output. In that, those inputs are okay. If what kind of skin tissue, what kind of blood pressure, what age should a person have for it to correspond that the person would likely has diabetes. So we are going for fitting. So I'll click on fitting, and I'll also wait because it's going to come up with another pop-up, another interface, and I'll wait for it to load. Okay, the interface is loading. So let me share that one now. Okay, so you should see one funny looking diagram with the neural network. So this is the interface of the fitting tool. Now, if you are using MATLAB earlier than, because mine is 2022B. So if you are using MATLAB earlier than 2022, the interface you see might be different. So it might just, that one actually is more straightforward. It's like a wizard. So you'll be moving from box to box. You'll be clicking next until you get to the end. So, but it's still the same principle of what I'm doing. So depending on the version of MATLAB you have, you might see a different interface. But if you just understand what we're trying to do, you should be able to navigate the different interfaces. Now, the first thing we need to do for the neural network is import the data. Now, that would present a problem because the data we have, remember I showed you the first 8 columns are the data, and the 9th column is the targets and the labels. Now, for you to use a neural network toolbox in MATLAB, you have to define the data separately and the labels also separately. So we have to do that first in MATLAB and save it to the workspace or before we import it, or you can save it as different files, then you import it. So let us just save it to the workspace. So I'm going back to MATLAB now. So you should be seeing my MATLAB command window. Now, what I want to do is I want to read the data into MATLAB, then create 2 variables and separate them from the targets and from the main data. Now, let me call the variable of the data my data. You might have to zoom in to see my screen. My data, and I'm going to use a function in MATLAB called read matrix. So read matrix can be used to read CSV files. It can be used to read Excel files, TXT files, and so on. So if I say read matrix, I'll just put the name of the file, diabetes.csv, inside the bracket. But however, I need to enclose it inside single quotations to show that it is a name. So when I click enter, in my workspace, my data would appear. And if you look at my data, you will see that it is 768 by 9, meaning we have 768 rows and 9 columns. Remember, the main data is the 8 columns and the target is the 9th column. So now I need to separate it into that data and the targets. So let me call the data maybe diab data, just to stand for diabetes data. Diab data is, okay, it's within my data, which I'm defining, but inside my data, it starts from I want all the rows. Remember, in MATLAB, if you are trying to index a matrix, the first number is row, the second number is column. So if I want to take all the rows, I just put a colon there, comma, then the columns I want column 1 to column 8. So this is the syntax. My data, open bracket, colon, the punctuation mark, comma, then 1 colon 8, close bracket. So when I click this, you'll see that diab data on the workspace has changed from 768 by 8, not by 9 now, which means I've eliminated the 9th row. So I have diab data, which is only the data without the target. Now I want to define target data, or let me call it diab target. No, diab target. And that would be my data because it is contained within my data. I still want all the rows, so I'll put a colon, comma. But in this case, I'm not taking a range of column. I only want the last column, which is the 9th column. So if I put 9, that should suffice. And when I click enter, you'll see that diab targets in the workspace is 768 by 1. So I have successfully extracted the data, the 8 data, and the target, the 1 target. If you like, you can save these separately into the workspace, then import them later on. But since they're in the workspace, I don't need to save them separately. So now what I can do, I can now go back to my neural network toolbox, this one. And the first thing we need to do, as I said, is import the data. So when I come here, I click on the import arrow and I click on import data. So it's trying to bring up a dialog box. And the dialog box, okay, I need to share it again. So I need to share. Okay, maybe what I should do instead of doing this, let me stop sharing and just share my window, my entire screen. Okay, so can you still see the small dialog box I'm moving around?
Yes, we can see.
Okay, so it's in this dialog box that you need to import now the data. After clicking import data, or let me do that again. Let me cancel. I come to import, click the arrow, then I click import data. When I click import data, it should bring up the dialog box. This is the dialog box. Now, if you look, you can see predictors and you can see responses. Predictors, responses. Predictors is the main data. Responses are the targets. So if I go to the predictors, I now select diab data, which is 76 by 8. Then in responses, I'll select the 768 by 1 diab targets. Now, I have now imported the data. I've specified which data I want to import. Now, if you look down, you see observations in columns and observations in rows. you need to change this back to observations in rows. And I'll tell you why. If you look at diab data, it says it's an array of 8 observations with 768 features. The target is 1 observation, 768 features. It is wrong. We have 768 observations with 8 and 1 feature respectively. So you change it to rows so that it now becomes 768 observations with 8 features and the same with 1 features. Then I click on OK. So it will try and import the data into the workspace. And it has now imported the data. If you look now, the neural network has changed a little bit. You now have 8 inputs and 1 output. Now, the next thing you need to do after importing the data, up here on the top, you will now see split. You will now see split. In split, it means you need to classify the data into training, testing, and validation. What percentage of the data do you want to use to train the model? What percentage do you want to use for validation of the model? And what percentage do you want to use for testing of the model? When you add the percentages, they should give you 100%. However, you can see that it has been made easy. If you change the values here, it can be so. So maybe if we're using 70% for training, I want to use 20% for testing and 10% for validation. So it's now 70, 10, 20. That's for the split. But you can use any ratio as you want. There's no rule of thumb. A lot of people will recommend 70, 15, 15, but you can use any one that you want. Now, layer size means how many neural network layers do you have? Do you want? Usually, the more layers you have, the more accurate. Yes, Mr. Murtala, your hand is up.
Yes, I have a question.
Yes, please go ahead.
So the trained data, does it always have to be the highest? Like,
yes, it's in most instances it has to be the highest. You use more data because you need as much data as possible for the training to make it more accurate. And you just need a little percentage to test to see whether, okay, the training was actually good or not. So some people actually go for training data, they go as low as 60, then maybe 30 testing, 10 validation, or 20 for testing and validation. But in most cases, the training data needs to be higher. Yes, somebody else is raising his hand. Go ahead.
thank you.
Okay. So the next part is the build. You need to specify how many layers. The more layers you have, the more accurate the training will be, because that means you have more neurons, more calculations, and the training will be more accurate. However, it means if you have more layers, it will take more time to train and it will take a larger computation. And also there is a limit that you can, if we say more layers means more accuracy, somebody, if he has a powerful computer, might want to use 100 layers. But the truth is, it gets to a point where even if you increase the number of layers, the performance does not improve significantly. So for our layer size, let's leave it as 10 as it is for now. After that, you can modify it to any value you want, but let's stick with 10. Now, after that, the next thing here is train. You have different algorithms for training. You have Levenberg, which is fast. You have Bayesian regularization, which is slow, but it performs well in generalization. You have scaled conjugate, which is memory efficient. So you choose whatever one you want to use. It's a design choice. I'll just go with the first one. So when you click train, it will take time to train. And more or less is trying to find a representation between a mapping between the inputs and the outputs. So let's give it time to train. Okay, so it's showing the training progress. The epoch here represents the iteration. Okay, and it has concluded. Usually for neural networks, the training process isn't usually as long as that of deep learning. For deep learning, you can train for hours, but for neural networks, you can train for a few minutes and you should be fine. So you can see the epoch, the iteration, it stopped at epoch 17 out of 1000, meaning that if it stops usually before the last epoch, it means no significant improvement was observed, and that's why it stopped. So it has it's showing the performance, the gradient, the validation text, and all that. But where you can look at the performance is here. You can see on the right hand side, you can see the training had 537 observations, validation 77, test 154. Based on the ratio that we divided it in, you can see the mean squared error. You want the mean squared error to be as low as possible. So in this case, for the training, the mean squared error was 0.12. For validation, it's 0.14. For testing, it's around 0.2. And you have the R value. You want the R value to be as closest to 1 as possible. So the R value here for training, you have 0.69, roughly 0.7. For validation, 0.5. For testing, 0.4. So if you feel this is good enough for you, fine, you can go with these results. However, if you feel, no, I can do better, you can adjust some of these parameters and train again. So let's increase the layer size to, let's say, 15 and see whether our performance would improve. Let me train again with, so it's saying training data will clear the existing trade model. Do you want to continue? Yes. So let me give it an opportunity to train again. It has finished. And from what I can see, the training, the performance has reduced because the R value is now 0.60. Before it was 0.69. Let me try 20 layers. And let's see what it will give us. So now it has gone to 0.66. So you can see that the more layers you add or the more things you tweak, the performance of the data would keep changing. So with 30 layers, I'm still at 0.64. So there's no significant improvement in the performance, whether I change the layers or not. And in some instances, the mean squared error has actually increased. Let me reduce the layers to 5 instead of 10. And let me see whether that will have an effect on the performance. Yes, Mr. Peter, I can see your hand. Go ahead. Yes, engineer, go ahead, please.
I mean, can you please give us the interpretation of this result?
Okay, the interpretation. Okay.
Yes.
As you can see here, we are looking at two major parameters, right? The mean squared error and the R value. The mean squared error and the R value. Now, for mean squared error, it is the square of the mean between the actual value that you have and the expected value. What I mean is, you know, we classified the data in training, testing, validation, right? In training, testing, validation. Now, for the training, you provide the data and the output. Remember, we classified training data as 70. We classified the validation data as 10, testing data as 20. For training, this 70% of the training data, which is 537 instances, you provide that to the neural network with the target. So the neural network will try to get the same target that the data set has. Whenever there's an error, the neural network will go back, adjust its weight, and so on, until it arrives at, to the best of its ability, the same values as the targets of the training data. Now, when you want to test, you do not give it the answers, just like how we do our tests and exams. You just tell it, okay, take this input data, give me results. And when it gives you the results, you now compare the results you've gotten with the actual results that you are supposed to have. So that is where the error value comes in. It's a difference between, okay, what am I supposed to get and what have I gotten actually? So, you know, sometimes the error can come in negative values. So you usually take a square of the mean. because you have multiple instances. So that is what MSE is. You want MSE to be as low as possible. Now, R usually is used in terms of regression models. And for regression models, if the value is closer to 1, it means the model is performing accurately. It is getting the accurate results, the same values as the, what are they calling it, as the expected outcomes. So the closer it is to 1, it means the more accurate it is in predicting these values. And that is why for R value, you want it to be as closer to 1 as possible. However, for the error, you want it to be as low as possible. I don't know if I've answered your question, Engineer Peter.
Sorry, is it? Can we go back to the raw data? That
okay. Okay, this is the raw data.
Yes, in this raw data, we are told it is a data set of diabetes patients.
Yeah.
Now, there are a handful of people who were tested.
Yes.
And the output result, that is from the last, I think is the I column, yes.
Yes.
I column, which is showing 1 and 0, either you have or you don't have.
Yes.
So from this table, somebody could pick it and look at it and say, okay, am I putting this into the neural network to determine for it to quickly generate the number of people with diabetes for me easily, or the number of people without diabetes easily? Is that why I am putting it into a neural network? Because I think you first of all need to, what do I want to infuse this into neural network to give me? What output am I expecting?
Okay. Okay. So let me explain in the context of this data. You know, for diabetes, for you to actually determine if you have it, you know, it's usually invasive. You need to test with blood sugar. But this is just to provide a prediction based on existing data. So you can have something similar like this for weather, something similar for the stock market. The whole idea for this is, you know, a doctor, if you come to a doctor, right, and you want to ask him, okay, do I have diabetes or not? Or I'm not feeling well, and he wants to check for diabetes. The doctor might ask you some of these questions. Okay, he'll check your blood pressure. What is your blood pressure? What is your insulin level? What is your body mass index? Now, from some of these informations that the doctor has, the doctor can now diagnose you and say, okay, you have diabetes. No, you do not have diabetes, right? So if, for instance, you want to use a neural network now to do that prediction for you in place of the doctor, the neural network itself does not have any medical knowledge like the doctor. So you need this data to train the network. So when you use this data to train the network, the whole idea is, okay, when somebody comes, somebody whose information is not here externally, and he now comes and wants to use your neural network to find out, do I have diabetes or not? The neural network will now prompt him, okay, put in how many times you were pregnant, put in your blood plasma, put in your pressure level, put in your age, and so on. When you provide this information, all you want is for the neural network to tell you, am I 1 or 0? And based on this data that you've trained the network with, it will tell you whether you are 1 or 0. That is the point of using the network in this context.
Okay.
Are we together?
Yes.
Yes. So when you train the network with the data, the performance of the network that we are looking at, the mean square error, the R, is just to show you, okay, using the data, how accurate is this model using that data? But when you are done training and you deploy the model, if you want to use the model, now when you're using the model, you don't know the class you belong to. or if you have some information, you don't know the class that information belongs to. So you just put it into the network, and based on its knowledge that you've trained it with, it will tell you this belongs to this or that. So it's a similar application when you're looking at facial recognition. You have 10 people you want to enroll. You collect their features, you train them in a neural network. So whenever somebody comes, whether the person is part of the initial 10 or not, if the neural network takes in the data, it can tell you, okay, you belong here or you do not belong here. It's the same thing if you want to identify a ball. You have 100 instances of balls, you provide the data and train the network. When somebody brings in something else and the neural network checks, it will tell you, okay, this does not correspond to the data I have learned. You belong to class 0. So that's more or less what you need the neural network for. And in terms of the modeling and identification we talked about, when you train a system like this, like, okay, if you have this data and you are asked, okay, develop an equation that maps these 8 parameters to an output so that you have x1 maybe plus x2 minus x3 will give you this. At the end of the day, it will be very difficult for you to do that because the data is many and it is not linear. But when you train with a neural network, you can now have that neural network as your model, mapping that input to the output, and you can integrate that model into a larger system. For those of you in power, for instance, if you want to develop a controller for the power system you are considering, sometimes you might not be able to model the power line or the network you're considering accurately, but you might have data, maybe from TCN that you have. So instead of you looking for a way to model the power line, if you already have the data, then you can use a neural network to be your model, and you can integrate it with the controller so that you can carry out the control analysis. So these are some of the importances of the neural network. So going back to our initial system, so when you look at the performance and you're happy with the performance, the next thing you have is to export. But before you export, you can generate different graphs for result purposes. You can look at the training state. When you click it, it will generate a plot for the training state. It will show you at what iteration, at what point did it acquire the best value and did it decide to stop training. So it's still generating the plot. Then after the training state also, you can look at the performance, the error histogram, the regression model, and so on. So there are different plots that you can acquire depending on the type of information you are looking for. So this is showing you how the gradient, that is the change in the error values, the change between the actual value and the error value. Sorry, the actual value and the acquired value, that's the error, has been reducing. At which validation checks, I think at epoch 17, that was when the training stopped. So you could see that the validation checks here, this is when it stopped. This is when it had the lowest error value and when it stopped. And if you look at the mu, which is the change in the performance, more or less, you could see that from here, there was no significant change in performance. That's why it was straight, and that is why it had to terminate at some point. So you can look at the different plots, see how you can interpret them. And when you are happy with the plots, usually this is just for reporting maybe your thesis or a paper or something that you want to include them in, then you can generate code or export model. If you are generating code, you can generate a script, a MATLAB script that sometimes if you develop the neural network using the toolbox, but you have a bigger code that you are using a MATLAB script, you can now generate a script of the neural network to use to integrate with that, or you can export the model to Workspace. You can export it as a Simulink block, or you can export it as a function for MATLAB coder. So if you generate simple training script, then you should be able to get a code of the neural network on how you can integrate it into your work. So this is more or less how you can develop neural networks. I think this thing is still loading for script generation. So let's see if it will come up. But this is more or less what you need to do if you are developing neural networks. As long as you have the data, then you can just simply use the toolbox in MATLAB to train a neural network. It's that straightforward. It's not as complicated as deep learning when you come to deep learning, because in deep learning, you have to specify the size of the layers, the types of layers, the kind of input output you'll be acquiring, and so on. Oh, it has generated the script, if I didn't know. So this is the script. So you can use this script. You can use this in a larger code. You can save it, and it can generate. This is a training script, so it will give you. If you run this script, it should train and give you a neural network. So this is more or less what we have to cover today. Do you have any questions? So if you export to workspace, what you actually be getting in the workspace is a neural network in the workspace. Let's see if it will come up. It should be net. Okay, it's exporting. Okay, so let me save it as results, and you can see the results here. So it's more or less a neural network as a struct. So you can see network training results. So you can bring it in and use it in your code whenever you want.